Howdy folks, I'm just going to do a shorter topic today called logarithmic differentiation. And logarithmic differentiation is not the same thing as doing the derivative of a logarithm. So in logarithmic differentiation, what we're doing is we are generally going to be applying extra logarithms. A lot of the times you don't have logarithms to start with when doing this method. In order to do one of two things. So the things that you can do in logarithmic differentiation are basically take something and cause it to be more simple derivatives than they currently are by using logarithm rules to split it apart into simpler pieces. Or you would be using logarithmic differentiation to be able to deal with the fact that you may have a variable in both the base and the exponent. If you have a variable in both the base and the exponent, we don't actually have a logarithm rule, or sorry, a derivative rule that will allow us to deal with that right now. So what we're going to do is not deal with it from the point of view of doing derivatives. We're going to change it and then deal with it using rules we already have developed. So I'm going to just jump right in because there isn't a whole lot of stuff to really talk about, because you'll see by using all the same stuff we've already developed how this is going to be used by going into some examples. So this particular function isn't overly awful. So f of x is equal to, and it's two binomial chunks to different powers up in the numerator, and a third binomial chunk to another exponent down in the denominator. If we were to just go at this using normal derivative rules that we've already come up with, start out with quotient rule. I'm going to have a product rule when you do the derivative of the top, chain rule for both the two pieces in the product rule. When you go to do quotient rule and finish off or have the derivative of the bottom, it would be not quite as bad. Just have the single term with chain rule, and that's not that bad. I'm going to give you a different way to approach something that looks like this, and you'll be able to tell what kind of qualifies as something that would break up nicely using logarithmic differentiation. So let's just get right into it. So when I use logarithmic differentiation, I personally choose to use the natural logarithm because it has the simplest derivative. So as we saw last time, log base c of x is basically going to be 1 over epsilon c, and so you have this little extra constant kicking around in the denominator if you are to take a base that is not e. And so the base e logarithm is what we call the natural logarithm, or ln. And so that is what I choose to use because the derivative of the natural log of x, or ln x, is just 1 over x. So no other constant needed. I'm going to start off just by writing down this function so I can see it as I'm working on it. And from there, I'm going to take the natural logarithm of both sides of this equation. So we have the natural logarithm of, and I'm going to choose, last time I did a little bit of an aside where I showed you that the derivative of the absolute value of the logarithm of the absolute value of x is the same as if you don't have an absolute value there. Because I might like to be able to describe the logarithm of this, the derivative of this function when it ends up being negative values, I'm going to actually place an absolute value around both sides of my equation and then perform the logarithm on it. Because the original two expressions on either side of my equation are equal to begin with, if I place them inside an absolute value, it of course doesn't change the fact that they are equal to each other. So I'm going to have big absolute value there, x plus 3 to the power of 5, 3 minus 4x to the power of 7, all over 5 minus 1 to the power of 3. All right, so on the right hand side, as a focus for a moment, this thing over here is I'm going to take the absolute value of it before I put it into the logarithm if I'm kind of following order of operations. That's going to get rid of any possible sign that would be there, so it's just the size of the thing. If I choose to do more absolute values, to write it a little bit differently, and what I mean by that is I'm going to actually take each of these binomial pieces and I'm going to I'm going to put them inside of their own. I'm a little bit messy there because I forgot what I was doing. Put them inside their own absolute value brackets. So if I am to do that, I get something that looks like this. And the reason why I'm doing that is because I'd like each of those pieces to go and carry its own little absolute value with it as we go forward. So on the left-hand side, I still haven't really done anything with it, and that's fine. The funny thing about logarithmic differentiation is all the work is done up front before you do the derivative. So we haven't got to the derivative yet. I'm still not quite there. I'm going to take that right-hand side still, and I am going to perform the step that's going to make it kind of a little more clear as to why we're doing this. So I'm going to break this up into 3 separate logarithms. So when we see pieces that are multiplied together, then they become addition of 2 separate logarithms. We also have a divided term here, and that's going to become subtraction of a separate logarithm. And if you remember from Pre-Cal A, doing that particular set of steps, we can do it all at once. And we also, at the exact same time, have exponents that are kicking around on each piece. And there is another logarithm law that allows you to take exponents and write them down front instead. So I can do this all in one fell swoop. So I'm going to put the 5 down front. Going to say the ln of the absolute value of x plus 3, and then plus the 7, that's the exponent on my second piece, moved down front, the ln of the absolute value of 3 minus 4x, and then I have minus the 3 moved down front, the ln of 5x minus 1. And so I have performed all the logarithm laws in order to break this up into smaller pieces. Now the reason why we're going to do this is because each one of these pieces now is an incredibly simple derivative. And so now, at this point in time, I'm actually going to take the derivative of both sides. Now that might seem peculiar because on the left-hand side, I have just f of x inside of a logarithm, not f of x plain. And the goal here is actually to find the derivative of this function. So I want to find f prime at x. So what I end up getting here is a logarithm's derivative is 1 over whatever's inside. In this case, it's a chain rule times the derivative of the inside. So what I'm looking for is that f prime of x, and I'll get to have that in just a moment. But I'll have to move the 1 over x onto the other side of my equation. Whoa, my equals is a little bit funky there. All right, so what I'm going to do now is take the derivative of each one of these 3 separate pieces that we have written apart from each other here. So we would get 1 over the inside. The fact that it's inside of an absolute value doesn't matter. We proved that last time. The absolute value basically will go away. And then times the derivative of the inside, which is just 1, and then times 5. I probably could have changed it just as I went. I'm going to change it now to a 5. So for the next one, I'm going to say that the derivative of the inside, I see it coming up. It's going to be negative 4, and then it's going to multiply with the 7 that's already there. So what I'm doing is I'm kind of looking at this piece here, knowing that what's going to happen because of the pattern of my last attempt, and it's going to mix together with the 7 that I have in front. Actually, if I wanted to be really sneaky, I would notice that that's going to be a negative 4 and 7 will give me negative, and then 28 over, and then 3 minus 4x, because it's 1 over whatever's inside, times the derivative of the inside, which is the minus 4, times the 7, which is the constant multiple out front. Next up, I'm going to have the 5 from this part right here, and the 3 from this part right here, the negative 3, I guess. So I'm going to have minus 15 over 5x minus 1. And so the derivatives there are very short and very straightforward. You don't have to remember what part of the middle of the quotient rule that's currently now doing a product rule you are on. And because of that, you're a lot less likely to get lost in the middle of one of these, and that's the main benefit of breaking it up. You might not prefer it this way, and that's okay, but it does give you another option. And for kind of the final thing, I'm going to say f prime at x is equal to, and my f of x gets multiplied up onto the other side, and then I have all this junk still there. And what I really should do, and I will have the patience to do it this time, although I don't really want to, and I have the same sentiment as my students usually there, is the f of x, it is written in terms, it is written in terms of f of x at the beginning of this problem, but I'm going to actually write that down. So it's x plus 3 to the power of 5. This is going to be a little long one. All right, so the end result is f prime of x is equal to x plus 3 to the power of 5 times 3 minus 4x to the power of 7 over 5x minus 1 to the power of 3, and then still all times this stuff that we found as the derivative on the other side. And I know I went off on your screen because I have it cut weird. I'm going to just move that over, and I'll cut the f prime of x off on my side. I'll almost fit it on there. All right. So that is logarithmic differentiation on one of these clumpy examples where we could do it another way, but I chose not to. All right, so next up, I'm going to show you what this would look like on an example where we can't really do it another way. So if I start off by saying f of x is equal to x to the power of sine x, right away, this is going to have some pretty funky behavior if I'm not careful about what x is allowed to be. It's going to kind of define itself, but I'm going to say right away that basically here, my x has to be 0. If it's not 0, I'm going to find that, or sorry, not positive. If it's not positive, we're going to have some real big issues because you're going to have negative numbers to the power of values that are oscillating between -1 and +1. And anytime those can be expressed as fractions with of the lowest fraction or the simplest fraction that has an even denominator, you're going to be getting like squares and fourths and sixths roots of negative numbers, which isn't going to work out. So we can't do that. We'll see that if we graph this thing afterwards. It's only going to be defined for positive values anyway. So since it's only defined for positive values of x, I don't have to be as careful with absolute values, so I'm not going to. Let's go ahead and see how this thing would go. So we have f of x. If I take the ln of it, it's going to be equal to, I should be careful actually, because my function could end up giving us, no, it's positive. No, I'm wrong. So it's going to be fine. I was second guessing myself there for a moment. I can write without absolute values on that side too. And so I'm going to have the natural logarithm of x sine x. All right. So at this point, I'm going to apply a logarithm law on the right-hand side that allows me to take anything that's written up in this exponent piece and write it down front instead. So in this case, I'm going to get sine x ln of x, and I have ln of f of x still on the left-hand side. I'm going to now take the derivative of both sides of my equation. So the derivative of the natural logarithm of f of x is 1 over f of x times the derivative of the inside, which is f prime at x, and that's going to be equal to, on the other side of my equation, that is now a product rule. So it's going to be sine x times the derivative of ln x, which is 1 over x. So I'll just say sine x over x. Plus, for the other part of my product rule, I'm going to take the derivative of sine x, which is cosine x, and then times the ln x. That's going to be left alone this time. Now, just moving over the f of x piece, f of x is actually x to the power of sine x. I'll switch it back so I don't have to rewrite it one more time after I'm done, like I did last time. And so it gets sine x over x plus cosine x ln x. All right, so it's kind of a little bit messier, but this allowed us to actually find the derivative of something that has a variable in both the base and the exponent. Now, just as an aside, because I get this happening every year, x to the power 4 is a power rule. 4 to the power of x is an exponential function, and x to the power of x is neither. It is, I suppose you could say it's both, but it doesn't follow the rule of power rule functions, and it doesn't follow the rule of exponential functions either when doing the derivative. So the way that we deal with that is exactly what we just did above. So we did logarithmic differentiation. We brought the exponent down instead as another factor, and because of that we can use product rule and just do normal derivative stuff from there. So just as kind of see what this looks like and if we did an okay job, I'm going to switch it over to a graphing scene here, and we had x sine x to begin with. So, oops, nope, we did not. We had x to the power of sine x. And so we get this lovely little thing, kind of nifty. So as I said earlier, I kind of second guess myself, but the function is always positive, so we don't need to worry about the absolute value on the left side of things. And of course it's positive because you're taking values of x that have to be positive and then just raising them to some power, so they will stay positive. All right, so that's what it looks like originally. I can actually in Desmos define this as being f of x some function, and I can say f prime of x is equal to this, and it's really smart. It does that, I believe, numerically for us. So it will show me what the derivative looks like. Now, I'm going to get rid of the original for a moment, just so it's a little cleaner, and I am going to write the equation of the derivative that we found. So I'm going to call it g of x just for the time being, and that's equal to x to the power of sine x times sine x divided by x plus cosine x ln x. All right, so it's getting, it's not so happy once, right? Wants me to do it this way, maybe? Yeah, all right. And what we see here is that the function that we came up with and what Desmos thinks should be the derivative of x to the power of sine x are in fact the same thing. So this worked in this case, it works in other cases too. So if you have a variable base and a variable exponent, we're going to use logarithmic differentiation to take care of those types of problems. So the main thing out of all this is, hey, you can take logarithms of things in order to clean them up before you want to take a derivative if you want to, if you have clumps that are being multiplied and divided. You can also do this new thing of variable base, variable exponent. And you're going to need to make sure that you take the time to really clarify for yourself the difference between a variable only in the base, a variable only in the exponent, and a variable in both of those positions. And if you can sort that all out, you'll know when to use what method, and you'll be good to go. All right, so that's it for today.